consulting career in 45-year consulting career in water resources that brought me around the world. So I worked extensively in Asia and across Canada. So lots about water.
Irina.
Hello, everyone. My name is Irina Micheli. I am a judge for the first time here today. I don't have any connection, any personal connection to the University of Ottawa, but I do work in the process engineering group for Canada Post, and that's how the connection has been made. But I'm out here in the Mississauga location, not Ottawa. So thank you. I look forward to seeing everyone and seeing what everyone has to present here today. So thank you.
And Chetram.
Good morning, everyone. My name is Chetram Jarbazad. This is my first time as a judge as well, along with Irina. I'm from Canada Post. I am a project director working out of Toronto at our parcel processing facility. Our connection with the University of Ottawa, I guess Canada Post in general, our head office is in Ottawa. We are one of the big co-op hires for the region. And I know we do hire a lot of co-ops, and for a lot of them from University of Ottawa. So our experience, both Irene and I, on mail processing, in sort of parcels and packets and letter mail, everything there is, and then getting it delivered all across the country.
So if my stuff doesn't come, it's who do I call exactly? Is it one of you two?
You can call me. I'll leave you my number.
And I don't think David, the fourth judge, are you here? So if you don't mind, I'm okay with us getting started. We'll have some inevitable glitches. I'm sure we'll use this spare 5 minutes. So the Pelicans, team D11. So judges, can you find your judging form for the Pelicans? Alan, are you ready? You're muted, Alan, but okay. And that's on that note, if you are not presenting, please leave your microphone on mute. I will do the same thing. If you have a question, stick it in the chat, and either Mohammed or I will be monitoring the chat. So Alan, do you have your form ready?
Yeah, I'm good, thanks.
Irina, you good to go? Chetram? All right, well then Pelican team, you have the floor. Team D11, the Pelicans.
How about me? Can you hear me?
Yes, we can, sir. We can hear you, sir. I'm just going to share my screen. Go. Share. First one. All right, thank you very much. Am I in frame, everybody? Okay, my name is Evan Kerr. I'm joined here by Jan Staszkowski, and we will be presenting the final prototype for our THEC. Okay, so the problem and our solution. Our problem was created to address the sizable environmental impact of residential climate. Heating, cooling, and powering residential buildings is responsible for 20% of all greenhouse gas emissions in the United States alone, and our current air conditioning and furnace options are unsustainable and costly. We set out to design an alternative method of regulating temperature without the need for fossil fuel source electricity, instead harnessing the Earth's constant heat reservoir and utilizing renewable energy, resulting in zero emissions. So our target user. We are a perfect fit for all environmentally conscious and cost-conscious homeowners. The product is inexpensive, entirely self-sufficient, and low-tech with a simple user interface. All materials are cost-effective and sustainable. Consequently, this product will reduce the user's monthly energy bill by eliminating power demand and relying on solar and geothermal energy. Now you may be asking, what sets our design apart? Firstly, the PVC piping inside the main box unit is made of vinyl and is easily bendable. The winding shape of the piping offers more surface area for a higher rate of heat exchange. We incorporated 2 fans into our design to increase airflow and allow for faster heating and cooling. Our heat exchange chamber would be made from an environmentally friendly concrete alternative, ground granulated blast furnace slag. This material retains all the beneficial properties of concrete, such as a high thermal mass, while also being made from recyclable materials. Finally, our entire electronic system runs off of solar energy. The prototype alone, which is 1/10 the size of the actual model, is valued at only $100 with a heat transfer rate of 172 British thermal units per hour. We will now switch over to the live demonstration. Please hold for a moment. There we go.
Okay.
I'll give it
So
to Jan.
if we begin here at the air intake unit, this is where the air is sucked in by our first fan. And the air is then taken from the air intake unit, is passed through the piping into the main heat exchange chamber, which contains a bendable PVC coil. This is where all of the heat exchange occurs, and the air is warmed up to the ground temperature that is constantly around at around 10 degrees to 16 degrees Celsius. Afterwards, if we just move here, here we have the first one temperature sensor inside of this pipe. It detects the air that the temperature is currently at coming from the box, while a second temperature sensor determines the temperature of the air within the house. Next, the user may determine what is his or her ideal temperature by configuring on this user interface their ideal temperature. And then once the temperature sensors detect that the temperature is at the correct temperature, the fans located at the intake and the outtake will turn on. This entire system is set up. It is powered by solar energy and a small lithium-ion battery.
That's great. Are you done?
Thank you very much.
Is that the end of your demo?
That was the end of our demo. Thank you
Judges,
very much
go ahead
for
with the
listening
questions.
to our
Please try to finish on time, guys. I don't want to be rude, but I will be.
Okay.
Judges, go ahead. Irina, did you have questions? Alan, did you have questions? Chetram?
I'd just like to ask them to restate how this works in a sentence or two. What is the end result of this and how could it be used more widely?
The end result of this is that the user saves money because this system effectively is like a help to the air conditioning units in many of our houses. And it lowers the cost. Sorry, did you ask how it could be?
I can say.
Yeah.
Okay, so yeah.
So since
Yeah,
it
no.
replaces some of the necessary power used for the AC, it will overall lower the monthly energy consumption. This means lower emissions as well as a lower cost for the homeowner.
Okay, that's good.
Irene, and you have a question?
Yes, I do. So will this aid in the use of an air conditioning unit? Will it be used beside it or will this replace?
Yes, so it must be used in tandem. Unfortunately, the temperature in the ground is not necessarily the best temperature for the inside of a house, so it would work in tandem, but it would greatly eliminate much of the power needed.
Furthermore, if I may just add, so yeah, it is in tandem, but basically the main goal of this system is to diminish the monthly energy consumption of the user.
Would you be able to estimate how much of a savings one may expect?
Well, given the fact that our current system is at 1/10 of the size and it works at 172 British thermal units per hour, if we would scale it up to a full size, it'll be around 2,000 British units per hour. While the average house or room needs, I believe, how much? I believe it needs about around 10,000. So it could diminish it by up to 20% if I'm not mistaken. But those are just off the top of my head.
Okay, thank you.
Where is the extra heat coming from again? Explain the process.
The extra heat, sir?
Yeah.
Well,
Okay, so the box will be 6 feet down where the ground temperature is more or less constant year round. We then have the box surrounded in clay and the air inside will hopefully be at the same temperature as the ground. When the air is heated to the same temperature as the ground, we will use that new temperature of air to pump in and change the temperature of the house.
Okay. So have you looked at going deeper and the cost effectiveness of going deeper to get warmer into warmer underground conditions to do the trade-off?
Well, we didn't, but just off the it wouldn't necessarily cost more in materials because it would simply require the elongation of the air intake and the air outtake pipes. That being said, it would be more costly because digging deeper would require more manpower, and that would probably rack up in the installation fees.
Yeah, so we based our prototype off of the online patent by Mr. Hernandez.
Good.
So it would be at around a depth of 2 meters in Ottawa, Orleans. Of course, this would vary because certain regions have a lower permafrost level, or not permafrost, but just a region of the ground where the temperature is constant, and that could be higher or lower in places.
Good.
Perfect. I stuck a note in the chat. I didn't give a bit of a blurb. I guess just as a background, we are looking at projects today for a heat exchange designer. Maybe you want to just talk a little bit about the overall project in a few words, just explain the context for the work.
The context of the work.
Or I could help you.
Sorry, I don't understand by the context of the work.
So
like,
the client, you didn't really explain what the project was all about at the beginning. You just sort of looked into your solution. So I could talk a little bit about that. Essentially, they're designing a heat exchanger, which is a chunk of space in the ground. And the idea is that the earth stores energy, and we're going to tap into that energy somehow, right?
Correct. We're very sorry.
That's okay. That's fine. And
That should have been in our second slide.
so just I put a link in the chat a little bit about the sort of the client proposal. It's a one-pager, but basically all of these proposals are different designs of a heat exchanger to take heat sort of from the earth into the house, and there's various issues with that, right?
Yeah.
Yes.
Lovely.
Correct.
Okay, so the next group is Team D21. And so judges, you have 2 minutes while Team D21 gets sets up to fill in your forms.
Thank you, Team One.
Thank you. Very
so
nice
much.
job.
Have a
Nice
nice
presentation.
day.
So once again, while the judges do their marking, Team D21 Pandora, are you ready to go?
Yes, we're ready. Do I have permission to share my screen?
Yes, go ahead. And the previous team judges was Team D11.
Right.
This is Team D21 setting up right now. So you might want to put it in slideshow mode. Perfect. So again, I'm going to start for each presentation. I will start a 3-minute timer. It'll be in my video. You can be able to see it. So please try to finish on time. Otherwise, I will have to cut you off, unfortunately. So 3 minutes, right?
Excuse me, I'm just going to stop sharing and I'll be turning it back on real soon.
All right, judges, are you almost done? I'm getting a nod from Irina. I can't see Alan. I'm getting a nod. I can't see you. Chetram, are you good? All right, well then, team D21, Pandora, you have the floor.
Thank you very much. Hello, everyone. So we are Team Pandora, and we're proud to present our product, which is aiming to provide a sustainable heat source for the household. And it is presented by Fahima, Mustafa, Kayla, and me. So this is a sketch overview of our final design, which has been improved multiple times based on previous client feedback. So for here, to keep it low tech and sustainable, we mainly applied a tubing method inside of the heat box to maximize the conducting surface area to increase the overall efficiency of the product. So this is our physical build of the product, and later after I'm done with this presentation, it will be demonstrated by Mustafa. So we use a hair dryer to stimulate the temperature inside the box. And air is pulled into the system from the air inlet and return vent tube by the 12-volt DC fan. And air will go through the system. This graduate change in temperature until the output is reached where the final temperature is measured. And here's the control system. We basically control the output of the temperature based on different temperature we received from the input. And here's the cost and lesson learned. There's the table on the right side is our bill of material. And honestly, we should have started building the prototype a bit earlier. That leave us time for more contingency plan, and we would carefully spend our budget more carefully. And here, Mustafa will carry on for a live demonstration.
Sorry, okay, perfect. All right, so this is our system. We have a blow dryer, which is heating the bottom of the system. And over here, we have our piping network. We have the heat exchange chamber and the temperature on the ground. And we're using a fan to take out the cold temperature in the system and blow it out in this pipe. And that's where we'll get our final temperature. And over here, you can see our temperatures, which are 1.6 degrees outside. And the reason I'm gonna have to turn that on when I get the temperature. Each of these thermometers. Over here, we can see that our temperature outlet coming out of this pipe is greater than the temperature that we have over here, which is the air inlet tube, which is connected to the weather outside. And basically, we see from this project that our system was a success because the temperature outside is converted to a higher temperature when we're getting the temperature outlet, which is 15.1 degrees.
Nice demonstration. Is that the end of your presentation?
That is the end of it.
Team D21? Okay,
yeah,
judges, questions? Go ahead, Alan.
Just go back and fundamentally describe how the foundation of the process. How does the heat exchange work in plain, simple terms?
So we have a heat exchange chamber filled with water. And from the heat exchange chamber, there's piping, which the pipes are transferring heat energy to the fan. And basically from the fan, we're blowing out the cold air in the system and blowing out into here so that we could get our final temperature, which was 15.5 degrees. And the reason why we heat up the ground is because we want to make sure that the temperature coming out is being heated rather than the temperature being cold. We kept our heat exchange chamber at temperature of 20 degrees, which is room temperature. And we tried to keep a temperature of 23 to 24 degrees for the ground. And basically, our goal was to, from the air inlet pipe, which was like placed outside using, and it turned out to be a success because our system gave a final output higher than the one that was outside.
Okay.
And the reason why we buried our heat exchange chamber 10 feet deep rather than 5 feet deep, which the client recommended, the reason for that was to get higher temperature below the ground, because when we're placing the temperature 10 feet lower, we found that it's going to be the temperature was going to be 24 degrees Celsius rather than 15. So that is why we placed it 10 feet under.
Did you do a cost effectiveness check? What if you went deeper than the 15 feet?
Well, when we looked into building our project, we found that we wanted to keep a temperature. We wanted to keep the ground temperature about 20 degrees. And if we went deeper, then we'd be getting a higher temperature than we were looking for. So that is why we stuck to 10 feet deep.
Okay.
It's not very intuitive, right? You got the winter, it's like minus 20 out there, and yet the ground is so much warmer. So that's the idea here, right?
Yeah.
Chetram, Irina.
I'll go ahead. Is there a concern or is there an idea of what material you would use to encompass this unit with it being that much further under the ground? Is there a concern with weight from 5 feet to 10 feet underground?
I'm not. Kai, would you like to answer this question?
Yes, thank you very much. I've been wanting for that. Yes, so right now what you see is made of plastic, which is just a demo. But for it to be buried deep underground, we of course going to use more sustainable materials such as the clay. Well, we're gonna use a clay and some on concrete, clay inside and concrete outside, and we. Oh, excuse me, you want me to start my video?
Fine.
Okay, I'm just going to continue. And with we also measure the deflation ratio to make sure that it doesn't crumble under the pressure of under the pressure of the soil on top of it.
Thank you.
Chetram.
Did you guys? I think you guys had a summary of the costs. That was, I think, cost of the prototype. But did you consider, I guess, with any of the solutions, do you guys look at the potential cost to the consumer to install something like, or to purchase one of these units and install it?
So can you repeat the question? I think I didn't quite get it.
You presented some costs and lessons learned. I believe that was for the prototype, but did you guys do any type of estimating what something like this would cost the consumer and the installation cost?
Well, I think the actual cost would be the same, but it would be around $10 less because it's the first time we're building the product, so there's a lot of test and experiment which add on extra cost. I think the actual cost would be for the real prototype that is concrete included would be around $150.
Nice. Perfect. Thank you very much, team D21. So judges, 2 minutes again, just to fill in the form, and then we will move on to the next team. D31, A Corp. Are you ready to go?
Yeah, I'm here. Should I share my screen?
Yeah, you start ready. Meanwhile, the judges, you can please complete your marking for team D21 Pandora. If you are presenting, I'm going to suggest you turn on your camera. It's much easier to listen to someone if you can see their face than if you can just read their name. Trust me. And again, Kai, if you have any video in your presentation or any sound, just make sure when you did that sharing, you check that box.
Yeah, I don't have any video.
Okay, perfect. All right, judges, how are we doing? Irina, you good? Chetram? You good? And John, Alan? Is that a thumbs up, Alan? Okay. All right. So team D31 A Corp. Go ahead.
Okay, so I can start now. All right. So hi, my name is Kai. I'm with Group 3.1, and I will be going through our heat exchange chamber that we have created. So the main problem is, well, the problem that we wanted to solve is to help minimize the cost of heating and cooling of the house. So this box would work to help heat the house in the winter and cool it in the summer, while not releasing any greenhouse gases to the environment. So our initial design was to put the pipes that go into the ground really deep so that we would minimize the footprint, but this would increase the cost of implementation, and overall it wouldn't be as cost effective as just putting them the regular 6 feet down. So this is just a quick diagram of our system, where inside the box here we have 2 sets of pipes. So one set would go into the ground, the other one will circulate through some type of thermal medium that will be in the box, and then those sets of pipes will go to the house, and there won't be any direct interaction. So as I said before, it's designed to help in the summer and the winter, and it'll be originally we were just going to run it off wall power, but then we decided to change it to solar and wall power. So yeah, so here's a photo of it, and then here's the electronics that we made. I'm just going to switch my camera now, so I can do so here on the we have a fan that'll be pushing air through the house side of the system. And then this box here contains all of our electronics, which we are running off of an Arduino. And then on the side here, we also have a battery. And then we also have a temperature sensor to monitor the output temperature of the air. And then we also have a water level sensor that will be inside that'll detect when there's water in the air pipes, and then we have a sump pump that'll pump all of that out. Yeah, I think that's pretty much it.
Are you done?
Yep.
Okay, questions? Judges. Irina, you start this time. Okay, Alan, go ahead.
Oh, no, I was hoping Irina would.
I'll go. Sorry, can you, I'll jump in back in. The installation of the unit, I'm sorry, did you say that you were going to do it vertically as opposed to horizontally?
So
can you explain that a little bit more?
Yeah, sure. Originally, we were gonna, the box was always gonna stay relatively the same place, about 6 feet under the ground, and that would just keep the temperature the same. It was the pipes that were actually coming out of the box that would go down into the ground. Originally, we were going to put them vertically, and that would help minimize the footprint, because we originally we looked into it, and a lot of people around the well, in Canada don't really have that big of a backyard or a yard, so we were trying to minimize the footprint so you could install it in a smaller backyard.
Thank you.
How did it's Al here? How did you decide the depth to go to get the right temperature mix for exchanging?
So we looked around at the frost level, mainly around here, but also in other parts of Canada, and we decided that about 6 feet was where really the ground temperature would stay at a reasonably stable temperature throughout the year.
Is it not better to go deeper and get a higher temperature exchange from down below? Because the deeper you go, the warmer is the groundwater.
Yeah, so it would, the temperature difference would be higher, but the problem with that is the cost of digging the hole would grow a lot faster than if you just put it about 6 feet under. And also, you would have to dig up. The thing with the pipes is they're usually spread out, and as they're spread out, you have to dig up a lot more earth. So only 6 feet under would be pretty good. But then if you went like say 10 feet under, you would have to dig up all of that surface area 10 feet under and then refill it all in. So it's more like a lot more work.
Mm-hmm, mm-hmm. Okay, thanks. Good answer.
Chetram.
I'm just looking at my notes here. Did you guys consider what was the overall cost of your prototype, and how does it translate in terms of your design? Translate to a more effective or a more cost-effective solution for the consumer?
Yeah. So the overall cost of our prototype here was, I think it was $96.50 something. We really wanted to try to stay within our budget, so we used a lot of the resources available at school. So the professor provided us with the concrete box, and then we 3D printed quite a few components to hold that together. And as for the full-sized one, we estimate it'll be about $5,000 to $10,000 to like install and construct the whole system for a full-size house.
Great. If that's all the questions from the judges, any more? Time for one quick one.
How much energy would you produce? Extra energy would you produce in a year from this system?
I don't think it would be that much. We would probably generate like 5 to 10% the energy, just because our system wasn't really designed with efficiency in like as our focus.
Mm-hmm.
It was more cost-effective way to like shave off some of that cost.
Mm-hmm. Okay, thank you.
Great. I think we have the client here. I don't know. You're labeled 94431675048. Are you the client?
Yes, I'm the client.
Oh, did you have any questions? You can jump in and ask questions too, but I didn't know who you were.
I'm Chinedu Enendo. That number has been, the number was allotted from the beginning of the...
You can change it.
Okay, I didn't know.
You can change it by renaming yourself. Did you have a question? I don't know your name, unfortunately. 944.
I'm Chinedu Enendo.
Chinedu, do you have any questions quickly?
No, not
Okay.
yet.
All right,
Yes.
Judges, please go ahead. And then the next team, thank you very much. That was a very nice presentation. That was team D31A Corp. The next team is team D12, and that will be Software Eddie.
We have the fourth judge too.
Oh, okay. He's arrived. Okay. David, are you here?
Yeah,
David Estrella?
I'm here.
So you know how to find the judging form?
Yeah, I got it with me.
Okay,
Yeah.
so you can start filling in the remainder. Don't worry about the ones you've missed.
Yeah.
So the next team up will be D12, which is SW Eddie. So D12, are you ready?
Can you see me? I'm here.
Yes, we can. We can hear you too.
All right, good. Hold on.
You want to start sharing your presentation while the judges finish their judging?
Yeah, that'd be good.
Okay, the previous team, once again, judges, was D31. This team is D12.
Go to this one right here. And then make this full screen. That's not a slideshow. Oh, whoops. Yeah. Guess we can start on this slide.
Yeah, we'll start at 10:30, right?
Yep. Okay. You can just say this, just this show off for now. All right. Oh yeah. Okay. That's.
And I've already forgotten your name, Chet, 944316. If you go into the participants list, you right click on your name, you'll see more, and then you'll have an option to rename yourself. Did you find it? I put it in the chat on how to do it. Chennai, I don't remember.
Chinedu.
Chenadu.
Yes.
So Chenadu, can you figure out how to do it? Mohammed can help you.
Yeah,
Okay, Mohammed, could you do it? You know my name. I've communicated with you before.
I can do it for you.
Thanks.
Okay, please. It's CHINEDU.
Lovely. No, I even know your name now. Nice to meet you, Chenadu. Okay, so Team Eddie, are you ready to go?
Yeah.
Go ahead.
All right. So hi, we're Team Sweaty, and we're here to present this. So it is more important than ever to address the issue of climate change. 25% of greenhouse gases, which deplete the ozone layer, can be directly attributed to HVAC systems that use fossil fuels and refrigerants. Furthermore, according to sustainable technologies, cooling and heating systems account for 50% of a building's total energy consumption. The goal of the THEC is to create a product that both helps the environment while reducing the amount of money used. So a lot of people want to help in the fight against climate change. However, doing so remains to be extremely expensive and out of reach for the average Canadian. The THEC system is here to help with this, providing a way to help combat climate change without spending a ton of money. The THEC will be the first affordable green household heating and cooling system, while the current systems, such as geothermal heating, remain to be extremely expensive and power consuming. The key aspect that makes our product better than our competitors is the use of PEX pipes. We have determined PEX pipes to be the best option when compared to PVC and copper. This is because the specs of PEX remain almost exactly the same as PVC while being less expensive than copper. The main advantage that PEX brings is that it can be bent with heat, reducing the installation time and labor drastically and saving both money and time. So to conclude, our product is a low-cost, eco-friendly heating and cooling system that draws minimal power. So now we can move on to our live demonstration. So we can just follow us around. Let's stop the screen sharing. Can you guys see that? All right, so we can start from here. This is our air intake box, which is above the ground. Connected to that is PVC piping, or PEX piping, sorry. It comes down underground and splits into 4 different lanes. If you follow me into this PVC box here, which actually makes it easier to install, we have our 4 horizontally laid out PEX pipes, which are actually bent here, if you can see that, to increase surface area to help with heat transfer. We come through the back. So this is the outlet connected to our sump pump here, which just collects excess condensation throughout our system. We come here, it connects to our box right here, which is our panel. You can control temperature with these buttons. If you want to come through, you can see all the circuitry inside. It all works. And we have these temperature sensors here. So this one's inside the house to record the temperature inside the house. This one is inside the box. And we've coded our circuitry so you can just set the temperature to wherever you want it to be, and it will do that. That's about it. If you guys have any questions, we'll like to take them now.
Very nice. Nice timing too. Judges.
We're going to switch to our member who's going to answer the questions.
Yeah. Tyler, are you there?
Yeah, I'm here.
All right, perfect.
For a typical house, how much energy can you produce?
Well, for a typical house, we're not producing energy. We're actually reducing the amount of energy that you're consuming. So given our calculations, because of how much power consumption, mainly it's the AC unit in the summer, but as well as the heating system in the winter takes up so much energy, you're reducing about, I think it was 75% of the power production, because all it is just the blower remains.
So you're saying you're reducing the energy cost by 75%?
Yeah, it was about that, because the AC unit uses almost was the main problem with the power consumption. And so when you eliminate the AC unit, but that, because during the summer, it is able to fully function by itself, where in the winter, it will need access help like a furnace, and it would still reduce the cost of the furnace usage.
Right. Yeah, it sounds like a lot of benefit out of it, but if that's the case, there's a market. There's definitely a market for it.
Yeah, for that, yeah, that's what we calculated. We're not entirely sure if our calculations are 100%, but it was about that.
Yeah. Okay, thanks.
Nice. Irina, Chetram, David?
I'll go. Did you guys estimate the typical cost for your units in terms of the consumer, the installation, like a real life?
Yeah, for consumer,
actual cost.
For actual cost, and scaled up cost, it still remains quite expensive compared to like an AC unit, because we calculated it'll be between 5 to 20,000 depending on the size of your lot and the size of your house, and also where you live, because in many parts of Ottawa, we are the Canadian Shield, of course, and much of it is built on bedrock, and so digging up bedrock will be much more expensive than a lot of clay that is also around here.
Irina. David.
Well, I guess my question is in the construction. How is this different from the conventional?
From the conventional, we also used a PVC box, which will be a little different than the traditional way, which would be a concrete box, which would take days to set and pour, while a PVC box will be able to be made at a factory and be able to be built in place within a day.
Oh, awesome. Thank you.
I have a question for you.
Go ahead.
How did you take into account the earth pressure when you're using a PVC box? Did you take into account the pressure from the earth, because you're 6 feet below up to the minimum, at minimum?
Yeah, we took into account that, and depending on the type of PVC and the thickness of the PVC, it was able to function under 6 feet.
Okay.
Just a quick question as well. Did you guys try actually turning on your unit? Did you actually test it out?
Yeah, we tried testing it out, and unfortunately we had a short in the circuit, which we couldn't find. So it kept turning on and off right now, but we were trying to fix that in the process. But it does, the fan functions, and online and through our circuitry online, it functions, but it's just a short in the system that's still causing us not to function at the moment.
Okay, thank you.
It's too bad. Okay, so that's the end of that group. That was team D12. So judges, please go ahead and do your marking. Dave, so did you find the marking thing? Good.
Yeah, good.
So the next team up will be Jeff, team D22. Jeff, are you here?
Yes, we are here.
Excellent. So you can go ahead and start sharing your screen and get ready. Again, if you have any video or sound, in your presentation, make sure when you share that you click on those two boxes. It's the green button in Zoom, right?
No, I'm sharing. I'm just trying to figure out which window it is. All right. Unfortunately, this thing isn't delayed. There we go. Everyone seems to be in the way of my beginning to this. There we go. We can all see this?
Yep, we can hear you too. So you're ready to go in a minute?
All right. Is it okay if we just point this out ahead of time?
No.
Okay. Okay.
You get 3 minutes.
All right.
One thing though, I do note, if you are going to do a live demo, just remember to stop sharing your screen and spotlight whoever is doing the demo and speaking. That way we'll all see you big rather than some little insight. I'm trying to do it in real time, but it's easier if you do it, honestly.
Yeah, that was just what we're going to point out. We under my name, Isaac, we have a camera on our prototype currently, and that's what we're going to be doing for.
So just remember when you're done with the slides, stop sharing, and then I can spotlight Isaac.
Okay. Yep.
All right. Are you ready to go? Judges, are we ready? I'm getting thumbs up from Ellen. Okay. Everybody else, David, you ready? Irina?
Yep.
Okay. Go ahead, team. This is team D22, Jeff.
Hi, I'm Isaac from Team Jeff.
And I'm Yusuf.
So today we're going to go over our geothermal heating unit, the THEC. If you currently look under my name, we have a live video of our prototype actually currently functioning. We're currently in a library, so it's not quite running full scale. However, it is functioning. Our understanding of the problem is that the patented design of Charmanu is to replace current heating and cooling systems in houses, is currently unable to provide sufficient heating in winter to heat homes to a comfortable range. The system also needed to be renewable, not contribute to the production of emissions, and low energy. Our system has all of these points, allowing for savings on electrical bills and gas bills while providing a positive environmental change. Compared to current HVAC systems, which require heat pumps and antifreeze to preheat or cool homes and still require additional heating in winter, our current systems are more energy dependent and cause more environmental damage if there is a leak.
Our system relies on renewable solar energy to provide electrical and thermal needs of our system. Our system captures thermal energy in water and stores in a hot water tank we call the thermal battery. The thermal battery is to improve the reliability of our system in situations with a lack of sunlight, such as night or on a cloudy day. The water of our system is circulated by pumps running off solar panels. We also plan to implement thermoelectric plates to increase the efficiency of our system by converting lost thermal energy into electrical energy to power the pumps. These plates would be installed on the solar panel and on the thermal battery to capture lost or excess heat. Our prototype focused on the heating and thermal components of our system. We did encounter some setbacks and difficulties, such as the thermal switch we plan to use as a thermostat was incompatible with the circuit, so our circuit was changed to run constantly. We also do not see the best results in our solar water heater effectively heating water, which we attribute to poor choice in materials and inexperience on our part. However, our final prototype was able to maintain a 17 degrees Celsius output, far from the ideal output of 20 degrees, but shows promising results and hope in the technology. While considering the client's needs, we also sought feedback from potential users and experts.
Firstly, the water in our system needed to be cleaned and well sealed to prevent buildup in the pipes and reduce corrosion. Additionally, the solar water heater should be located at the top of the roof on the south side. Lastly, when being installed in existing homes, there is the potential of damaging the homes during installation, making expert installation required for this product. Our design incorporates the current design of the client with a solar water heater and thermal battery to provide reliable additional heating in winter. Our design is well thought out, reliable, efficient, and environmentally friendly. So I will stop sharing such that it's a little bit easier to see our prototype. We currently have a fan blowing up through vertical tubes in the THGC, which we did not fill with water, again, because we are in a library. And then we have our pipes here with our pump running and a thermal battery up the top here that's coiled around our air tubes in order to provide the heating. Well, again, we're in a library, so it's not quite running as we would intend it.
Nice. Any questions from the judges?
So I have a question. So the unit itself, the coils that would be in the unit would also be surrounded by water. Is that?
In the client's patented design, which we are basing like all the existing components on, so the THEC, the thermal medium, and so on, they state that is going to be a water clay mixture. So that is what we're planning. However, for the purposes of our prototype, it was cheaper and more effective just to use water.
So is it still going to be, what distance, I guess, is it going to be sunk in the ground? And what is the purpose, I guess, of the clay water mixture? Assuming the full, not the prototype, the full unit.
Yeah. So again, we're going back to as described by John Manu in his patent. So the THGC will be buried 6 feet underground, where ground will be at temperature equilibrium, and then the giant concrete box is going to be filled with the clay water mixture. Does that answer your question?
Kind of. So the solar panels are going to be used in doing what?
So
what's the purpose?
So the solar panels, their purpose is to provide the energy that the system is going to be consuming. So for our system, it's going to require a fan or furnace blower to direct the air through the system and into the house, as well as a sump pump and a regular pump to circulate our solar water heater. So the two pumps are going to operate off of a set of batteries and solar panels, such that they do not require like the power grid in order to function.
Thank you.
If you were applying this to a house instead of a prototype, would solar energy still be sufficient to run the system?
In our early calculations, yes. And I believe one of our teammates here, Bowen, can confirm those results.
Yes, so we did the calculations based on our prototype, and we transformed the size from the prototype to the actual house. It does work. And we also, like in my house, we do have like a solar water heater, something like this installed, and it does work. It looks great. And the purpose to have the thermal battery underground, it's to have better installations. So it's underground, it's in the winter, so underground is better. So we have the thermal battery underground. So let me know if I have any more questions.
Jetram, Dave?
Yeah, so my question again is regarding construction. So what would there be any benefits using your system compared to the existing? I mean, to the conventional, in terms of construction and in terms of operation?
So it's a very simple system. So all a user would need to interact with would be a thermostat, ideally. Additionally, in compared to a conventional HVAC system, it has a lower footprint as per design. And it's like, it will reduce your gas costs as you don't need a conventional like gas furnace to heat the homes and etc. So it just reduces your energy costs, your gas bill, and compared to other systems. And yeah, I hope that answered your question.
Perfect. Chetram, do you have a question?
Did you guys consider the overall cost of the unit to the consumer? That would translate up to a full-scale solution?
Yes, I can answer that. So the cost for the system is around $10,000 to $20,000. It really depends on the size of the house, the location of the house. We did consult a contractor. So he mentioned to us there's potential cost to reinforce the roof. So, and based on the location, there like different geological situation, the cost could be different. And
all right.
yeah,
I'm going to cut you off there, Bowen. Sorry. That was team D22. That was Jeff, right? So judges, please go ahead and mark your scores. The next team up will be D32, Chads.
There you go. How do you think that?
Chads, really? Sorry.
Okay.
Again, folks, if you have any sound or video in your thing, make sure you've checked those boxes before you hit the sharing button.
Okay.
Hello and welcome to 3.2 geothermal heating exchange. Let me show you how it works. Our geothermal system is composed of three main parts. First, we start with the intake.
Oh, we're not ready to start yet, guys. Can you? Yeah.
Oh.
Okay. Judges, are you good to go?
Oh, yeah.
Okay. So again, that the one you were marking was D22. The next team is D32, Chads. And Chads, when you're ready.
And please, guys, move your camera slowly.
Okay.
Hello and welcome to Team 3.2 geothermal system. Let me show you how it works. The system is composed of three main parts: the intake, the thermal exchange chamber, and the outtake. Let's start with the intake. In the intake, we have a few important parts. We start off with our fan, our drainage control the whole system, a solenoid valve, a return air pipe coming from the inside, all of this going into the thermal exchange chamber, and then going into the outtake. Kate, my partner, will explain more about the thermal exchange chamber.
So the chamber itself is made of concrete. The air is warmed through conduction from the slurry to the pipe, and then through convection from the warm pipes to the air traveling through the pipes. Inside of the heat exchange chamber, there are two pipes to allow for maximal surface area to move to warm more air. The two pipes combine into one before exiting the system and traveling through a sump pump to reduce moisture, and then the warm air exits the pipe into the house. Now, here's a video of the solar panels automatically rotating towards a light source. So that's the video of our solar panel. And now we'll have my colleague Tristan show you guys the geothermal heat exchange chamber and tell you guys about what sets our heat exchange chamber apart from the rest.
So our heat chamber actually has something very interesting. It's Bluetooth controlled. So using my phone, I open an app on iOS and Android called Bluefruit Connect. Using Bluefruit Connect, I can connect to the Bluetooth module over here, and we will see the Adafruit Bluefruit LE, and we can know that we're connected by seeing a blue light turn on right here. The blue light's now on, meaning that we have a Bluetooth connection. Now using the UART command module, I can actually, but first before I do that, I must remove the temperature sensor from the thermal exchange chamber and put it in hot water to deactivate the auto system. This takes about 10 seconds to update. We will hear the fan turn off temporarily. The fan is now off. Now, if I send the command open, the fan is now on. And now if you look over here, the fan is now on. And now if I simply use the command close and it's sent, the fan is now off. Now I'll return the system to automatic by setting auto. And then now I will bring the temperature sensor back into the thermal exchange chamber. And in a few seconds, it will adjust to the temperature. Additionally, our Arduino also has the auto command. Using the auto command, it takes a look at the three different temperatures across the system: the intake temperature, the thermal exchange chamber temperature, and the outtake temperature. The fan, this Arduino compare temperature between the intake and the thermal exchange chamber And it will know that if the thermal exchange chamber is cooler than the outside, it will turn the fan on, and so on will drive on. As an emergency system, we have a 10 amp hour battery right in here, as well as a solenoid valve, which is a power outage. Was the video not on?
No, he was filming himself.
Yes, he was. So unfortunately, your time is up, but it was nice to see your face through the whole time. Give us a quick glance of what we were looking at. Just show us really, really quickly. We haven't got any time, unfortunately. There we go. Okay, judges, question.
You're filming yourself again.
Yeah, it was very nice. Yeah, it was beautiful. We like watching you.
Am I still filming myself? Jesus.
Yes, you are.
Feel like
Now
I'm
you're
old.
not. Judges, questions. Go ahead.
How much energy does this save in a typical house?
So by having the automation, we save a lot of energy because let's say at night it's colder and during the day it's warmer. We can save a fair bit of energy. Kate, do you have the exact number? Unfortunately, we do not have the exact number, but
75%.
But we save about 75% of cooling in each room that has this thermal exchange system. Scaled up appropriately, obviously.
Yeah. That's a lot of savings.
Well, again, scaled up appropriately. This is a 25 scale. So we would estimate that it'd be increased by 25%, obviously.
Okay.
You had showed us a shot of a picture of the inner workings of the unit, and the coiling was kind of scattered. Was that by design, or was
that was by design? Basically, our goal was, let's say, I'm going to just draw it out right here for you. We have basically one pipe that goes like this, and then we also have the other pipe that goes opposite to this to really increase the surface area. Instead of having them overlapping, just other than this exact point right here, by having them more scattered, we have more surface area for the air to, exchange.
Okay, thank you.
Jetram? Dave?
I really like the automation part. Is there an app for that?
Yes, there is right here. Let me show you. By simply using the app called Blue Fruit Connect on iOS and Android, I'll go right here and I'll just deactivate the automation by putting it in hot water. That's it. But by using the app Blue Fruit Connect, so you see it turned off right here, I connect to the Adafruit Blue Fruit LE, and then I go to UART, and I simply send the command open, and I send it, and then the fan turns on. And then I can also send it to close, and then it turns off, and then I can set it back to automatic. And then by setting it to auto, I can simply take the probe and put it back into our thermal exchange chamber, and there we go. And then we can tell it's Bluetooth connected right here by the blue light.
That's interesting. Thank you.
Jetram, did you have a question?
Did you guys consider or estimate the cost of this unit for a typical consumer? And what would be some of the factors that affect the cost?
Well, what I would start off by saying is this actually costs us less than the $100 that we had on budget.
So, but sorry, I guess the scaled up cost of an actual unit.
Yeah, we scaled it up. We found that it'd be anywhere between about $5,000 to $7,000, depending on how performant you really want it to be. By having maybe more than just one fan, you can have more of a performing system. But we've ranged between $5,000 to $7,000 Canadian.
Shanadu, you have a quick question? Shanadu, rather, do you have a question?
No.
Okay, well, judges,
Yes.
you have 2 minutes, and then we will start the next group. Thank you very much, team D32, the Chads, I guess. The next team will be team D13. So judges, if you want to finish your scoring, then we will get on with the next team, which is team D13. But that team was D32. Team D13, are you here?
Yes, we are.
Okay, you want to start setting up so you're ready to go?
Sure. I'm hoping everyone can see my screen.
We can.
And now I'm hoping everyone can see my face as well.
We can.
There we go.
And again, once again, if you have any video or sound in your presentation, just make sure you, before you hit that share button, you click those boxes. Did you do that? Ayushu?
Yes.
Ayush, did you click the 2 boxes before you hit share?
The 2 boxes. No,
So
I did
stop
not.
sharing and then look, see where the sharing, see the 2 boxes, the check boxes?
Okay, share sound and optimize for video.
Yeah, so if you have video or sound, make sure those boxes are checked before you hit share. Okay, it says you're sharing. And you want to be in slideshow mode, obviously.
Yes.
And all those little, we see gray boxes, any pop-up over the top, we see as a gray box. So that's a gray box right on the middle of your slide there. So just get rid of it. And the ones at the top as well, if you can. And then you're going to go in about a minute. No pressure. Perfect.
Can you guys see my screen now?
That's perfect. Yep, that's perfect.
Okay.
All right, so judges, are we ready to go? Hang on. Judges, give me a thumbs up. Irina says yes. Chetram, ready to go? Okay, so the next team then is team D13, the Hot Pockets. Go ahead.
Okay, good morning, everyone. My name is Ayush. I will be the presenter representing Hot Pockets today. Okay, those are our team members. And brief overview of the project. So at the start of the semester, the client expressed the need for a heat exchange chamber to be created. This led our team to empathize with the client to understand the situation. A final functional prototype was then created, which will be presented today. It is important to solve this problem so that inexpensive, eco-friendly heat exchange chambers can be created. The current solution to this problem is our prototype, and alternative solutions will be prototypes presented by other groups today. So this is a general overview of the final prototype. I will show a video later on explaining all the different aspects of the prototype. And I wanted to talk about why our prototype is the best. And the reason behind this is because it has an optimal pipe configuration. The prototype also consists of a temperature-activated fan, such that the user can set the house at the desired temperature. The fan will only turn on and off if and only if the fan is not at the desired temperature. This strategy proves to be very economic since less electricity will be used. And here you have an LCD display, which can be switched off on and which can also be switched off at will. And it is very economic since we'll be saving power. And if we're not using it, we can switch it back off. And finally, the prototype also consists of a filter. There we go. A filter that prevents air from getting polluted. And just as I showed before, this is an overall design with all the components included. Now I will share the video of the prototype in action. This is the optimal pipe configuration inside the heat exchange chamber. It is where all the heat exchange happens. And then here we have our Arduino connected to the LCD, where we can control the temperature settings and the LCD display, along with the fan with the filter. Here we have the fan functioning without the filter. And then Oliver in the video will be toggling those knobs. This is the one to switch off the LCD display, and the other one to control the temperature setting so that the user can set up the temperature at the desired setting. And the fan will stop if and only if the temperature is not at the desired temperature, thus saving power. So that's it for me. Thank you very much for your attention. And if there are any questions, I'll be happy to answer them. Thank you very much.
Nice timing. Judges. Go ahead, judges. One of you.
How much would this cost to be upgraded to a full normal house, say a 2,000 square foot house with a 1,000 square foot roof?
It would cost in the range of maybe $4,000 up to $10,000. That's the estimated cost it would take to actually scale a project up. The prototype itself was in the range of $95 to $100, which is very less considering this, like it is not a full scale project. But if we were to upscale it, it will be somewhat expensive.
And how much energy do you save with it in a typical house?
We would save about roughly, not much, but 9 to 15% of energy.
That sounds reasonable. Do you think it could be higher with a better design? Could it ever go up to 50, 60% savings?
Yes, it would, but this depends also on how deep we bury the prototype. And according to some, theoretically, every 100 meters we go down in the ground, the temperature increases by 3 degrees Celsius. So if we go down by 1 meter, that means the temperature would increase by 0.03 degrees Celsius. And so if we want higher efficiency and more energy saving, we would have to go deeper. And to go deeper, we would have to use materials that would be able to sustain a lot of weight from all the surroundings around the box. And so this would put a lot of cost onto the final prototype. It's essentially like the upscale project. Because if we were to have more energy and save more energy, we would have to pay higher, essentially, to use the right materials.
Irina, Chetram.
If the unit, you said the unit goes from anywhere from 4,000 to 10,000, that's quite a large variation. What would you be getting on the low end at the 4,000, and what would then make it 10,000 at the higher end? Is there a difference in design or a difference in options?
Yes, the answer would rely on efficiency. The 4,000 one would be less efficient, meaning that it would cost less, but it would not save up as much energy as the one at 10,000 would. The 10,000 one would have materials be able to sustain a large amount of weight, all while being efficient and saving a lot of energy. So the answer to the question would essentially be that the 4,000 one would not be able to be buried too deep underground while providing very less energy efficiency, while the 10,000 one would consume less energy to function, provide more energy efficiency, and sustain more weight. That answers your question.
Bertram?
How deep was your system in the ground?
Sorry, I didn't quite hear you.
How deep was your system in the ground?
So it would be about 6 feet underground.
And that saves about 10 to 15% of the energy.
Yeah, yes, it does, because at 15%, the reason behind this is that the average temperature at ground level is 12.79 degrees Celsius. So if we go about 6 foot underground, that's about 1.83 meters around. And so the temperature inside the chamber would be about 23 degrees Celsius, which would really save about 15% on a good day.
Thank you.
Dave?
I'm good for now. Thank you.
Chetram?
Did you guys have any lessons learned from the work you did?
Lessons learned would be that we should really keep our budget in mind, because we have had to change stuff up. Initially, we planned to create our prototype with aluminum, considering that it is a very non-ferrous, made of non-ferrous metals and lightweight, good strength and corrosion resistance. But then it proved to be very, very expensive to be included in our design. So the main thing that we learned was that we need to create our bill of materials very effectively, so that we don't run into troubles down the road. But because we're not creating a total upscale working prototype, but rather it's a small prototype, just relating the concept to the client.
Nice. On that subject, Chinadu, the client, do you have any questions?
No.
Okay, lovely. Thanks. So judges, that was Hot Pockets, Team D13. Please go ahead and do your voting. The next team up is D23, the Avocados. So all these puns are so good. Avocados, are you ready?
Yes, sir.
So D23. So if you have any, again, if you have any video or sound in your presentation, make sure you've checked that box before you hit the sharing button.
Just curious, I have another one of my group members over there. We're gonna have two people that we're gonna switch between them.
Okay.
So his name is Philippe. So in the middle of the presentation, when we get to the live demonstration, please click over there because I'm gonna stop sharing. And I'm gonna stop sharing my screen as well. Everyone can see it, right?
Yes, we can see your slides. What was the name of your friend again?
Philippe.
Philippe.
So,
Okay, so
Rosier.
once you stop sharing, I will try and spotlight Philippe.
Awesome. Thank you so much.
All right. We'll start in about a minute.
Oh yeah. Also, if you guys want to look more at like the bill of materials in detail, please check over our Maker repo. It's linked to the actual design day scheduling. And yeah, that's all. Can't wait to
Maybe
talk to you
someone
guys.
on your team could put it in the chat for us.
Yeah, I'll put it for you guys right now. I have it open.
Otherwise, you ready to go at 11:10?
Yep. Here you guys. Oh, sorry.
So once more, the previous team was D13 Hot Pockets. This next team judges is team D23, the Avocados.
Okay. So,
All right, judges, are we ready? Am I getting a nod from anyone? Chetram, Irina, okay, good. Alan, you good? Okay, excellent. Go ahead, guys.
So, hi everyone, my name is Al Tatar. I'm going to be the one mostly representing Team Avocados for our thermal exchange heating chamber. And we decided that the major problem that the client proposed to us was that he wanted an environmental friendly way to use geothermal energy to cool and heat a Canadian house during the winters and summers as efficiently as possible. So pretty much the problem can be broken down into three major sections: the affordability, the compactness of it, and the low emissions rate that it needs. So as you know, and it's been mentioned a lot during the previous presentations, current geothermal heating systems, they're all really either expensive, extremely large, or very low emissions. So what we decided to do is we decided to bring the original design that our good friend Mr. Chandu did, and we decided to bring it in and make it adjusted, because we believe if something isn't broke, don't fix it, right? So we decided to add stuff to it to make it so that it works functionally with the Canadian industry. So what the THEC system is what we didn't actually change is that we have a major box, and in this box we have piping systems that have as much coverage as possible to keep a constant temperature, with a return pipe to return the air from the house back into this heating system. We have a sump pump that removes the actual moisture from it, just to make sure that nothing happens and nothing bad goes wrong, especially since we have circuitry, live circuitry and live resistors. And that's pretty much the generalization. Now, a lot of the other solutions that have been proposed, this was Chandu's, a lot of the stuff we found was that a lot of them went really deep into the ground, heated up, and then went back into the house. But we believe that the problem with that we find with this is that sometimes it might either overheat from the house, and it isn't as per se similar to what the client requested or the user requested. So what we decided to do is make a dynamic resistor heating system, or DRHS. Now, what the dynamic heating resistor solution is that there is resistors with a specific wattage that as we run current through them, they heat up because of just basic physics. And what happens is that in this chamber, or as you can see with the conic shape here, is that it heats up and then it pushes the air out eventually. This is the generalization of the summary of the theory behind it. Cold air, 2 temperature sensors that actually make sure something works. And this is the THEC system, maximum coverage to make sure everything works. It uses cement just to make sure everything is enclosed. And when it is in solution, then nothing bad happens. So here's our live demonstration. Please control the video. Is it on? Yeah. Awesome. So here we have the full system here. We have the full. Sorry. Okay. So sorry about that. So pretty much, thank you. So pretty much as you have here, we have the dynamic resistor heating solution here, the full-on conic shape, which is the heating heats right around here as the cold air comes through here. We have our sump pump here that we just modeled out of a and that serves the same purpose. Here we have a solution for our thing, maximum solution. As you can see, a lot of the thing is fully covered so that there's maximum heat exchange here. And this is our input. So the good thing about this is we have a button inside of the house that once clicked, turns on the actual, turns it on. And that's really good because not a lot of Canadians actually want to step outside in the actual winter. So we made these small adjustments just to fit the Canadian industry, and we believe it's one of the best solutions out there. So thank you so much for your time.
Nice. Judges, questions?
Okay, we're here now. Great.
I have a question. Can you explain the cone shaped?
Also, just really quickly, we have live data from our previous testing. If you guys would like to check that out, it's underneath the. I'm not talking. It's underneath again the presentation we linked in our Maker repo. Thank you so much. Please ask your questions.
Sorry, can you explain the cone shaped item? That seems, I think that's the only one we've seen this far.
Yeah. So
what was the purpose of that again?
So it's the dynamic resistor heating system. So the main THEC system is the one Chengdu had in his proposal, but we believe that it serves its function, right? We did make small adjustments to it where we actually made it a little bit deeper. So instead of it being around the 4 to 6 to 7 foot, we actually brought it down to 8 feet because based off our previous temperature stuff, and if we want to import this all across Canada, as you know, as the farther you go north, the colder and the steeper the frost barrier becomes. And we believe that 8 feet is the best estimate for that. So that's the first thing. So we didn't adjust anything there. But what the dynamic resistor heating system is an addition to the entry point of the house, where as the resistors heat up, it's like sort of at the entry of the house, and the cold air comes in. In the chamber, there's a fan, and the fan doesn't turn on, so there's no direct airflow as the resistors heat up. And once the inside, because there's a temperature sensor, like I showed in my diagram here, I'll go back to it because it's kind of important. As you know, it heats up here as the cold air circulates around it, eventually until the fan pushes it out into the home. And because it's dynamic, what it means is that depending on the requested temperature, it actually adjusts the current that is required to go through it so that it functions properly.
Thank you.
Yeah, no problem.
Why would I buy your system for my house?
Why would you buy our system? Because we believe it's the most it's the least first of all, it's the least hands-on basis thing for you to do, because you simply touch a click of a button, or you need to simply touch a click of a button to adjust everything you need, and it automatically does everything for you. A lot of these systems, they're not really reliable, especially with Canadian winters, because the intake might be a lot warmer or a lot colder than you actually want, and you can't keep a constant temperature in a home, which is sometimes very vital, especially for if you have children running around the house and whatnot. But this system, especially because we actually made it really safe so that you can't actually reach your hands into anywhere, it's actually one of the best ways to fully heat up a house and to actually maintain it, as we believe so.
Ketram, David.
I'm actually intrigued by the title of your presentation, but what would be the advantage of your system compared to others?
Well, like I previously said, it's a lot hands-off, and it's all based off computers and circuitry and algorithms, less than actual conventional heating systems with coils and stuff, because it dynamically adjusts to it. And again, it's the same system that Mr. Chengdu proposed with his main constant temperature. And we know that works perfectly fine. As he explained, it was perfectly implemented in Africa and all the other South countries. But the problem that he was facing was, how do we heat it up, right? You know, adjusting as much as other groups did, where they adjusted the flow of it and how much the air was able to circulate. At the end of the day, that's not the problem. The problem is getting that perfectly constant temperature and heating it up to something the Canadians want, right? So that a temperature that the Canadians want. And that's what we offer. We offer a solution that actually is able to heat it up and maintain the temperature that's wanted in a perfect temperature for as long periods of time as needed.
Chetram, did you have a question?
Can you guys talk about your lessons learned through the process?
Oh yeah, of course. So this is our third prototype, and there was a lot of stuff that actually, because the dynamic resistor heating system is something we came up with. It hasn't really been implemented anywhere. We believe that it was an original important idea. So I'm a farmer. We use stuff like this for heating up like eggs and stuff so that they actually hatch. But we believe that we can actually import this to the Canadian homes as well to heat it up and maintain something, because it serves the exact same purpose, right? Maintain something that's hot and make sure it stays the same. But while coming up with it, there was a lot of problems we faced, especially with the idea of hot glue, because it is a heating system and it uses resistors that get really hot. So when we use resistors and we have hot glue in the system, as you can tell, a lot of it actually melted away and a lot of the sensors would fall down and stuff. So we actually decided that hot glue is a better one. Secondly, another thing we decided was gears and use.
I'm going to stop you there. Judges, please mark the team. That's team D23, the avocados, right? And the next team up will be D33. So we'll, judges, if you want to complete marking for D23, that was the avocados. Thank you very much for the demo.
Thank you for your
team
time.
D33, are you up? Ready? Anybody there from D33?
Yep, we are here.
Oh, okay, good. So again, if you have any video or sound in your presentation, just click those two little boxes before you hit the green share button.
Yep. Jazia is
Can everyone
presenting.
see my screen?
Yes, we can.
Okay.
Team No Name, right?
Yes.
So once again, judges, the last team was team D23. This next team will be team D33, but we'll start in about a minute. Are you ready to go, Jazia?
Yes.
Okay, so 1 minute. Chinadu, if you have any questions, you have to speak up.
Yeah. No, I don't have questions because I've been through, this
No,
is my first section with the students. So
you've seen them.
yes, it's just a repetition of what we have come up to now.
All right,
yes.
fair enough. Okay, Jazia, you have the floor. Judges, are we ready to go? Okay, I'm getting a nod from Chetram. I can't see anybody else. Irina, okay, good, perfect. Off we go.
Okay, so we are Team No Name. I will start by presenting a few slides, and then I think Zach will be showing us the physical prototype. So our main goal in this project was to be able to provide heating as well as cooling. We also worked on reducing costs, reducing energy consumption, and maximizing sustainability. So our heat exchange chamber would be made of concrete as suggested by the client. Concrete was chosen because it is highly durable. It has very good heat insulation and a low cost. Then we would have air running through PVC pipes. This was chosen due to its resistance to corrosion and once again, the low cost. We would also have solar panels that would be heating water. This water would be running through copper pipes, as we can see in the picture, to provide the additional heat needed right before the air comes into the house. Copper was chosen due to its high heat transfer and resistance to rust. And then one of our main ideas in this system was to be able to use also a closed loop in addition to the open loop. We thought using a closed loop more often would actually reduce the energy consumption. So the loops would be regulated by the house thermostat. Once set to automatic, the system would work on an open loop during the day and on a closed loop during the night. So it would be regulated by the presence of sunlight or the functioning of the solar panels. And this would especially be beneficial during the winter because at night the energy does drop a lot, so a lot of energy would be saved. Then we would have air filters. We would have 3 inner air inlets of different sizes going from largest to smallest, which would really ensure that nothing would enter the system and cause harm or alter the air quality, which could potentially cause health and safety issues. And the use of many filters would also prevent clogging. And then finally, we have 1 fan directing the air as suggested by our client. This fan would have 3 different speeds, also regulated by the house thermostat. If we're looking for more temperature change, it would go faster on a closed loop and then slower on an open loop. And then these are a few software models that we made and a sketch of our solution recapitulation. I think now Zach will be showing us the physical prototype.
Yes. So here is our prototype. I don't know if we can see this. This is the copper piping here. Now, in a prototype this small, we couldn't get malleable pipe small enough to wrap around this copper. So this is just a wire, but when it was built to a full-scale prototype, it would be piping and would run hot water through it. The piping in here would be going back and forth to ensure maximum heat transfer. The box is made of concrete to increase strength. If it were built to full scale, we would include rebar to maximize the strength of the concrete to not worry about issues as far as structural damage. Other than that, should be said.
Okay, that was nice. Judges, do you have any questions? Alan, do you have a question?
How deep is the box when it's installed? Yeah, I'm unmuted.
So for the size of the box, it would be changing depending on the house or the building that it would be providing heating or cooling for, but it would probably be like a few feet, 3 feet maybe.
Yeah, we were saying 6 feet in our calculations.
Mm-hmm. How much energy would it save when it's properly installed for a typical house?
So we found through our calculations that it would reduce your monthly bill by about 3% because it would increase or decrease temperature by 1 to 2 degrees, which isn't huge savings, but overall, because this system would be in parallel with the other system currently in use in the house, it would be beneficial in that aspect.
Did you guys maybe take a look at if there's a 3%, I think you said 3% savings, if you look at the cost of the unit, like me as a customer, how long would it take me to like pay this thing back?
Yeah, so the life of the system is estimated to be about 50 plus years. After 50 years, the concrete, we don't really have statistics on that, but the system to implement itself off the bat is around 12K, including excavation, the cement, the rebar, and the grading afterwards. And so we estimated about like 30 years down the road, it would be when you kind of come out even with it. It is a while, but it also, the system is meant to be used in parallel with others and not completely replace it.
Thank you.
Dave, do you have a question? Jethram?
Yes, sorry. In a typical house construction, what would be the initial cost to build this system?
Yes, so as stated, it would be 12K. We estimated 5K for the excavation. The cement is approximately $125 per cubic yard. And afterwards, the grading and the extra material in the rebar, and rebar is estimated to be about 20 cents per cubic. I forget the exact value there, but that was our estimate, and it came out to 12K in total for the full implementation at full scale.
And that's on a typical house, I guess.
Yes, that would be
Typical Ottawa house. Yeah.
Ottawa house. Okay, thanks.
Why wouldn't you make it deeper to boost the savings you're getting and get a shorter payback?
Yeah. The one thing in our constraints from the client was that he wanted to be not, well, he said it had to be between 10 and 6 feet. And so in our planning and after our first prototype and meeting with the client, it was stated that we went too deep. And so we had to bring it up a bit. And yeah.
It's more just finding cost savings that's important.
Yeah.
I think so. Keeping it at about 6 feet was the perfect medium.
Okay. Thank you.
I have a question. Hello?
Yes.
Yep, go ahead. We can hear you.
Yes. How you said that the savings was going to be approximately 3%. How did you arrive at this? Because it differs so much from what other groups have said. How did you get just 3%? How did you arrive at 3%?
So I can maybe show you our heat, because we did a heat transfer analysis within the pipes itself and the cement. And so that came out to be an actual just 1 degree difference. And then afterwards, we did some estimating with the kilowatts and how much it would transfer to afterwards in that aspect. And that's where we came up with the 3% number. It's about 2.93, but we rounded it up because
Would you have an idea of what you could do to improve on this efficiency to achieve higher percentage?
So if we could bring it lower and deeper down, and as well, if we could get a higher or create some sort of generating system to store the solar power energy so it's not just constantly used. And that would increase the output and the savings. But those would be the two kind of variables which we could play with to increase those.
Perfect. Chetram, did you have a quick question? We got to get on though.
No, I think I'm good.
Okay, lovely. So judges, that was team D33, I believe, correct?
Yes.
And this next team is team D14. So judges, if you want to just mark D33 and then team D14, are you there?
Hello, everyone.
Yes. Okay.
This
So
is-
you set up, Mohammed, get ready. So again, if you're going to share a presentation, make sure you've ticked those boxes for sound and for video if you've got any video in your presentation. And we'll start in about a minute. Do you want to practice your sharing, or are you gonna? How are you gonna do it?
We don't have sharing. It's okay. Yeah.
Okay. Ready to go? Judges, how are we doing? Irina, you good? Chetram? Thumbs up from Irina. Thumbs up from Chetram. I can't see you, Alan. Okay, I'm going to assume all the judges are ready. Okay, go ahead, Mohammed, when you're ready.
Hello, this is Yusuf Hamdan from Team Rocket. Today we will be discussing with you the heat exchange chamber. We will start with the air inlet. It is designed in from sheet metal. From sheet metal, it with a slanted top to prevent any water or snow accumulation, with a adjustable opening here. Coming from the air inlet, we will begin with the chamber box, which is a secure home for our piping here. We have a 3x3 layer with S-shaped piping that will perform the heat exchange. Coming from the air inlet, from the chamber box here, we have a outer pipes which will be split into two main splits. One will go to the sump pump, which the main goal of it is to prevent any condensation and prevent any water accumulation in our system. The other split will go to the furnace blower here, which consists of a fan. And the main goal of having the furnace blower is to which will be connected to electric system here to adjust all the temperature with a potentiometer, and the temperature will be shown here on the LCD, with also temperature sensors that will be usable for sensing the temperature inside the pipes and outside the pipes. And thank you for listening, and feel free to ask any questions.
Okay, judges, done early. Nice. Go ahead, Dave, if you have a question.
Again,
Irina,
I guess.
Chetram,
Sorry.
Alan.
How much energy do you save on this thing as you move it forward, if it was sort of implemented in a typical house?
You asked the amount of energy, right?
What's saving? How much would you be saving in terms of energy use?
Energy? Yeah. Well, we calculated for the heat transfer to be 8.4 joules per liter of air. So that's like the heat transfer that this system can achieve.
But you're replacing the energy going into an air conditioner or a heater in the typical home, right?
Yeah.
So if you installed that, how much would you be saving in terms of outside electricity or energy coming in percent? Any idea?
We don't have a percentage, but we have a value, which is for each liter of air that we're gonna like heat up, it's gonna be a save of 8.4 kilojoules.
Okay, okay. And what would it cost to implement it on a typical house?
It will between like $5,000 and $15,000, and it will vary. Like the variation will be depending on the type of house we have,
the lot size,
Yeah.
the area. But
that sounds like a reasonable cost for me to purchase, but I'd like to know, you know, how much saving I would be in real energy going into the house before I installed it.
Well, the system's supposed to be like a.
Well, the system, you'd be saving a lot more since there isn't, as you've seen, there isn't any, let's say,
heat pump,
compressors.
No fossil fuel.
There really is no electrical like components here except for the temperature sensors, but that's the only power source in this system. There is no compressors. There's no like a conventional HVAC system. You'd be saving almost entire of your, I'd say 90% of your energy, well, cost with the conventional system.
Yeah. Okay.
Rena,
Can
a question? Sorry.
I think you said my name. How does your design, how is it better than others?
Well, we have designed the piping system in a S shape here, with also 3x3 layers. It's also giving the air coming from the air inlet more time to have like better cooling and better heating.
Well, yeah. So what we did, we maximized with the box we have. We maximized the length of the pipes with this S-shaped configuration, and if you can see, we kind of did like 2 tests based to check out if our system works, and it does do, like we did 2 tests for cooling, and as you can see, when the temperature varies, it goes down from 22 degrees to 17. So that's like a difference of 5 degrees. So this is just saying that our system is functional, the design is working, since it's doing its job of cooling. Yeah.
I have a comment.
Okay.
Yeah, just a short one. I wanted to suggest to the students that it's important you're able to relate the data from your invention to a common in common terms. To be able to explain to someone who is not a technical person who wants to purchase this product how much you'll be saving in terms of real life, figures, like in terms of cost or whatever. I'm not just mentioning the power of the frames.
Classic cost benefit. Chetram.
I guess with regards to did you guys do any benchmarking to come up with your design? And are there any, I guess, background that how your design resolves the problem from your client? You didn't provide much of a problem, and you used your problem background in terms of what you're trying to solve.
Okay, so what we're trying to solve is basically the system, we want it to cool down in summer times when the inlet is open, let's say. We want it to cool, that was our goal of the system, is to cool down. And when it's closed in winters, it should be able to heat up. We only did the test, let's say, during the summer. And as I showed the graph earlier with our data we got with the temperatures, it is cooling down. So that's how we tested, that's how we know that our design, the 3x3 layers of inner pipes we did, is working.
Got it.
Yeah.
Dave, did you have a question? Last one, but not least.
On the S pipes, why did you use that concept?
So this is we tried a few other configurations, but this is what would maximize. So what we want is the length of the pipes to be the maximum length, right? Because the bigger the pipes, the more time the air will stay in the box. This is where the heat transfer occurs. So how we did that to maximize this length is this S shape. This is how we got the most pipes inside. The total length is about 90 inches with this prototype. But I would say in reality, this shape is the most efficient. Yeah.
Excellent. Thank you very much. That was Team D14, Rocket. And judges, you want to mark it? The next team is the last team. I have a request for the team that managed to video themselves rather than their prototype. I'm going to let them demo their product. But first, we'll finish the schedule, which is Team D34. Are you ready to go, Team D34? While the judges continue capturing the marks for Team D14. Thank you, Team D14.
You're welcome.
Team D34, are you here? Team D34, that's MENG, Meng, I guess. Team D34, are you here? We can't hear you, if you are. Is there anybody here from Team D34, MENG? Mohammed, do you want to just go hunt for them, maybe?
Yeah, sure.
Kate, which team were you again?
We're team. Sorry about that. We're team, I think 3.2. Yeah. Yeah.
Okay, team 3.2.
Team Chad.
Okay, Chad's okay. D32. Okay. If team D34 is not here, you might as well do your demo right now.
Okay, sure. Sounds good. Admiral, if you want to share the screen.
I will spotlight you. I wouldn't use your slides. I would just do your demo, my friends.
Okay, let's just do the demo. So I'm just going to remind you guys, so we are the team, our solar panels track the light source, and that's pretty much all that we had in the slides before the demo. And now Tristan is going to take it away and do the demo quickly.
So let me tell you how it works. So this is our system. It's composed of three main parts. We start with the intake right here, which is composed of fans. Solar panels are Arduino, a 5 amp-hour battery, as well as a solar valve, which brings us to the thermal exchange chamber, which is made of reinforced concrete for be extra strong, as well as a mixing chamber right here between the return air and the intake air, and then brings us out to the outtake where we have a filter right here to make sure that all the air you get is nice and clean. Let's start right here where we have our solar panels that track the sun within 2 photoresistors, and they find the perfect angle to get the perfect illumination from the sun and maximum energy consumption. So right now we can see that it's oriented towards the sun. We also have our Bluetooth module right here, LJ. You can come and show it over here. So I'm going to show you a little demonstration of our Bluetooth module. See, it's right here. So using an app available on both iOS and Android called Bluetooth Connect, we open it up, and then we simply will find the Adafruit Bluetooth LE. We press connect, and then we press UART, and then we can see by this blue light right here that it's connected to Bluetooth. Now, if we simply take our temperature sensors, which are found all along the system, and put it into hot water to deactivate the system, it will take a few seconds for the system to realize that the system is now closed. And then you can hear that the solenoid valve has closed and that the fan is off. Now, if I go here, I write the command open and I send it, the fan turns on, the solenoid valve opens and air goes through the system. And I can also close it manually. And now it's closed. That's simple. And I just put it back into the little hole and I put it into automatic. There we go. Now, additionally, I'd like to show you this. Our system has a 5 amp-hour battery that lets us run for 10 hours without power, which is very good because in the winter in Canada, sometimes we lose power for a long period of time. Now, let's say that we do lose power for more than 10 hours, the solenoid valve will automatically close itself to create a closed-loop system in case of it being very cold and we have no power to prevent hypothermia of the people inside. Additionally, our system has 3 temperature sensors, one inside, one in the intake, and one in the fuel exchange chamber.
And that's all we've got time for. Sorry. Okay, team D34. So hopefully that was good enough to get your point across. It was much better when we could see you. It's true. Do we have team D34, Mohammed?
Not yet. I'm trying to communicate with them.
Okay, we have they've got about 3 minutes, then we have to sort of pretty much end it. So D32, I hope that was long enough. To be fair to all the other teams, I didn't give you any longer in your demo than anyone else had. So it was not. It was nice to see that the other side of the camera, though. Thank you. So just for the judges again, that was a redo of the demo part of D32's presentation. We are still waiting for the last team, which is D34, MEng, MEng 4.3, what it says, to show up. And they were scheduled to go from 11:40 to 11:50. It's very unusual that teams don't show up for their demo. So maybe something has happened with internet or something like that.
Yeah.
I just emailed them.
Okay, well, we'll give them another couple of minutes, Mohammed, and then I'm afraid the judges will have to go and start deliberating rather. So judges, again, the previous team was a demo for, it was team D32 doing their demo. The previous team before that was D14. The last team to judge will be team D34, and you might as well get ready to judge them so that when they come in, you'll be ready to go. We'll give them another few minutes, and then we're just going to give them 0, and we will finish the session, which is a shame. Does anybody have any questions? Judges, did you have any issues or questions? No, I'm seeing shaking heads. Okay.
Yeah.
Alan, you good?
One of them is here, Dominic.
Okay, Dominic, are you ready to go?
Yes, hi, how's it going?
Okay, hi, Dominic. So start presenting. We're waiting for you.
Okay, yeah, sorry. I'm just going to open the slide there.
This is the last team. This is team D34, MEng 4.3.
Share screen. How do you share screen?
Green button. If you've got any sound or video, make sure you check those boxes before you hit that share button, though.
Where is the share button?
Green button at the bottom in Zoom.
Oh, yeah.
And don't forget those 2 squares, the check boxes, if you have video or a sound in your presentation.
Okay, I don't think we do. All right, can you see
whenever
that?
you're ready. Yep, go ahead.
Okay. So basically, yeah, we're a group 4.3. I'm here representing my group today because the rest had courses and stuff. But anyways, our main goal for the project was to have a green and efficient heating system for compact heating in houses around wherever. And then so basically we have a system based on Arduino R3 sensors reading the temperature inside of a house or a building, and then sending the feedback to the intake fan and the heater to I guess send how much power you need to get the correct temperatures in the house. So that's the design of a heat chamber. We have 9 tubes going vertically in the chamber, while we have the intake going down into a chamber and then passing through while it heats, and there's a fluid inside the chamber to actually do the heat exchange. And then the would go up, and then here, well, yeah. That's the dimensions of our pipes inside and outside. I'm not going to go over them because I don't have the time, but We use PVC because it was the cheaper for a prototype anyways. We use PVC for optimized system. We probably go with a copper pipe for a better heat exchange. And then if you add all the subsystems together, electrical with the ventilation and thermal, we get the solar panel running the fan, the Arduino, the thermostat, and the sump pump, so that we can keep the system green as possible. And then, yeah, if you can see here, we have the intake fan, solar panel, the case with the Arduino sensor and inverter and stuff. And then we have the thermostat and the sump pump at the bottom. Here we did some calculations just to see how much power we would need to actually run versus production from the solar panel. And we figured out that we only would need a small solar panel, so it wouldn't be too expensive, because the fan and that doesn't take much. For electrical simulation parameters, we found that the ideal would be between 16 and 18 programmable based on user requirements. Obviously, you could change the codes and make it different temperatures for different people. Flow rate, we found that was very efficient, our system being 180% more efficient, meaning the system is better than average residential furnaces without emissions. And then we have our bill of materials here at the end. We can see that the subtotal came to about 165, which is more than the watted $100 budget, but it was the best we could do for a prototype.
That's great.
Basically your system in 3 minutes.
Nice. Judges, quick questions.
I think you had some demo videos on one of the slides. Did we have? Do you have any pictures or videos of an actual prototype, or is it just the demos on the CAD?
I can open up the on-chip design. This is the actual system that we designed.
I think her question was, did you actually build it?
Mm-hmm.
No, we didn't, because we're all virtual. Like, I'm on PI myself. We have another guy that's in Toronto, and we have another guy in Montreal, I think. So we didn't find like the time. So we just actually did the detailed 3D thing. So yeah, no. We didn't.
Okay. Yeah. Can you run this one then?
Sorry?
Can you run this demo then? Sorry.
I don't think we actually have a simulation, to be honest.
Okay.
We just kind of built it.
Design. Sure.
Yeah.
Okay.
Dave,
Thanks.
Jetram, did you have any questions? Alan?
Did you guys do any type of cost analysis of the prototype or of the units, what it would take to actually scale this up and install?
Like for
and any type of energy savings assessment?
For prototype?
Yeah.
We did the build materials and stuff, like we did an optimized system, and then we did a prototype, like what we would have built if we would have all been in Ottawa. And then what we would have all built would cost around 150. And then I didn't do the whole part, so it's hard to, I didn't know the whole system, so it's hard for me to explain everything, but.
Yeah, fair enough. If you don't know, you don't have to answer. Any other questions from any other judges?
Were you able to figure out how much savings this would result in terms of energy use in a typical home?
Versus like a typical furnace or normal system? I didn't do the calculations and stuff. I actually just did the 3D modeling. So, but power concentration, power production. I I don't think we did it. No.
Okay. Okay.
unfortunately.
All right. Well, then Dominic, unless you have anything else you want to say, and judges, any other questions? Otherwise, we're going to adjourn to the breakout room. Again, that was team D34, MN 4.3. Thank you very much, Dominic, for coming. We got you in there. Nice to have you.
Yeah.
Thank you.
Sorry I was late there. I couldn't find the link.
No problem. It's okay.
Yeah.
And judges, I'm going to open up a breakout room now. Please go join it, and I will join you there. So to join a breakout room in Zoom, it's the blue button, right? And everybody else can stay here. The client can stay here and ask any of the teams that are still here questions. But Mohammed, I will leave you here and I will go join the judges in the breakout room. Thank you all for paying attention. And Chandu, did you want to say something?
Yeah, if I do not have questions, am I free now? Or do I
Yes.
have to wait until you're back?
No, you're fine. You have an evaluation to complete of your own, right? You know
Yes,
that.
yes, I'll do it at my time and sending.
Lovely. Thank you very much. And there's a
Thank
main
you.
session. I guess we'd like you to join us in the main session if you have time. Mohammed can explain the details for that. Okay, Mohammed?
Yep.
Alan, do you know how to join the breakout room?
So, Mohammed, I can leave now?
Yeah, for sure.
Okay, you're going to send me this like you used to?
Yeah.
Thank you. Bye.
Okay, nice to have you, Chandru. See you.
Thank you. Bye-bye.
Bye.
Have a good day.
Thanks.
Yeah, sure. But if you want to know about the results, I think it's better to stay.